want to crack that one. I just cracked that one. All right, so there's your linear speed. And so S is called the arc length here because that's the distance that you're traveling, right? Your arc length is your physical distance. Angular speed, however, is your change in angle over time. So the funny thing about angular speed is that two objects can have very different linear speeds, but they can have the same angular speed. For example, if you have a circle with a radius of 1 versus a circle with a radius of 5, if they both do one full revolution in a minute, let's say, then their angular speed is identical. They're both going around 2 pi radians every 1 minute. But the linear speed is faster for which one? Aiden? Right, the circle with the radius 5, because this one's only going around that circumference of a distance every minute, whereas this one's going around a much larger circumference. So this one is covering more distance in the same amount of time, and that affects linear speed, but you have to wrap your head around the fact that their angular speed is identical. You know those little things at the playground that spin around and the kids get on them, right? And there's kid number 1 standing towards the middle of it, and kid number 2 is standing on the outside, and someone whips the thing around. Who's going faster? Kid number 2, right? The one towards the outside. Their angular speed is the same, but linear speed, kid number 2 is going to get a lot sicker than kid number 1. Okie doke. You have a funny story about that, John? Oh, you did? Oh, who is your physics teacher that's showing you this? Oh, boy. All right. All right, so anyway, the transition is very simple. If you want the linear speed, you essentially take your angular speed and multiply it by the radius, which stands to reason why, again, if 2 people are going the same angular speed, this one's velocity is going to be 5 times that angular speed because his radius is 5, and this one's is going to be 1 times that angular speed because his radius is only 1. So whatever the angular speed is, you just multiply it by the radius. Now, you could think logically about a longer way of doing that, right? If you know your angular speed, you can figure out how far of a distance via your circumference, right? And you could try to figure out your entire distance around in whatever unit of time by calculating your circumference and doing really however many circumferences you're surpassing in whatever amount of time. It's just much quicker to do it this way. So if you just memorize that, you'll be better off. So in this one at the bottom, a wind machine has blades 10 feet long. I like diagrams. If the propeller is rotating at 4 revolutions per second, it wants us to find the linear speed. But before we do that, since the linear speed is the radius times the angular speed, now we have the radius is 10. We don't actually have the angular speed yet. We have 4 revolutions, right? That's 4 circumferences. No, not circumferences, I shouldn't say that. That's 4 full circle angles because we want the angular speed. So if you go around 4 times, what angle have you covered? What's the measure of your angle in radians if you've gone around 4 revolutions? 8 pi, right? It's just your 2 pi times 4. So your angular speed is 8 pi per second. And so your velocity just ends up being 80 pi per second, which if we want to change that into something that makes sense to us, that's 251.3. And our unit of distance is feet per second. Like I said, if I wanted to find my velocity a different way, I could figure out my change in distance, which would be 4 circumferences. So my change in distance, 4 circumferences, which would be 4 times 2 pi r for every second, and I'd still get 80 pi. Every circumference is 2 pi r. I have 4 of them, so that's my change in distance every second, and I get the same thing. Okay? So not a tough concept. Just takes some getting used to. It was brand new too, so we had to start there. All right? Make sure you memorize those formulas, especially the easy transitional one. I'm not so concerned with angular speed and linear speed because I think logically you can think about those. Okay. So your trig functions, you have 6 of them. All 6 should be familiar from last year. Sine, cosine, tangent, cosecant, secant, and cotangent. So if t is a real number and p is some point xy, is a point on the unit circle. So I'm just going to take a random point xy on the unit circle in quadrant 1. Whoops. This is angle T. Right? Who can explain why the sine of T is just the y coordinate? Why is the sine of T just going to be the y coordinate of that point on the unit circle? Okay, let's go back to SOHCAHTOA. Sine is equal to what over what, Mitch? Opposite over hypotenuse, correct, requires what kind of shape first? Right triangle. So if you drop this altitude to the x-axis, as we always do, what's the length of this leg in terms of our variables that we have here? Morgan? X. And the length of this leg, Nate? Y. And the length of the hypotenuse, Trista? It's a number, because we're in the unit circle. There's your hint. 1. So the unit circle has a radius of 1. So since sine is opposite over hypotenuse, that'll be y over 1. Hence the reason it's y. Okay? That y coordinate is only your sine value exactly if you are in the unit circle, because otherwise your hypotenuse wouldn't be 1, and so it wouldn't be over 1, and it would change everything. So for the same logic, your cosine is x, just your x coordinate of that point, adjacent over hypotenuse. Your tangent is opposite over adjacent, y over x, so your y coordinate over your x coordinate. And then these 3 functions are our reciprocal functions. The reciprocal of sine is cosecant, so 1 over y. Cosine is secant, 1 over x. And tangent is cotangent, x over y. Remember that? Okay. So, if we are given a point on the unit circle, then immediately we know that the sine of our angle is root 3 over 2. Because the sine comes from the y coordinate. Cosine comes from the x coordinate, so the cosine of theta is negative 1/2. And the tangent is y over x, which would be root 3 over 2 divided by a fraction. I'm going to keep change flip. Negative root 3. Not that I told you have to memorize these values, but just out of curiosity, do you remember what angle has a sine of root 3 over 2? Anybody? Nope. 60. Yeah. Pi over 3. But that's coming. Memorizing those is coming. Then your cosecant is just your reciprocal, but we will rationalize in the trig chapter, so that'll be 2 root 3 over 3. Your secant is -2, and your cotangent is -1 over root 3. Now, how do we make sense of the fact that some of those values are positive and some of those are negative? How do you know, or what's the other way we can say, oh yeah, it makes sense that the cosine is negative and the sine is positive and the tangent is negative? Remember your little trick? All students take calculus. Good. So this point, just based on what you know about plotting points, is a negative x coordinate and a positive y coordinate. So it's in quadrant 2. All students take calculus. That tells us that only our sine should be positive and our cosine and tangent should be negative. And then the reciprocals just follow suit with that. Remember that? Good stuff. Find the values of the 6 trig functions at an angle of pi over 2. First of all, where is your pi over 2 angle? Where's the terminal ray of that going to fall, Bailey? It's not in any quadrant. Mackenzie? Yes, it's like pi over 2 is like 90 degrees. So it's on the y-axis here, right? So what would you label the coordinates there if you decided to put yourself in the unit circle, which I think would be smart? What would those coordinates be, Bridget? Of that point. Like if this is 0, 0, how do I get to that point? We're in the unit circle. 1. And so once we kind of put that together, again, we can grab our sine as being the y coordinate, cosine as being the x coordinate, tangent being the y divided by the x, which is undefined. Do you remember that? Tangent of 90 degrees or the tangent of pi over 2 is undefined. And then your cosecant is also 1. Your secant is undefined. And your cotangent, rather than being y over x, it's x over y, so that would be 0. Okay, for both sine and cosine, the domain is negative infinity to infinity. You can take the sine of any number, you can take the cosine of any number. But because, for example, sine is opposite over hypotenuse, isn't the opposite leg always shorter than the hypotenuse? Right? So there's no way we can have a numerator that's bigger than the hypotenuse, which means there's no way this can ever surpass 1. Okay? Technically, if you still have a right triangle, an opposite side would never even equal the hypotenuse. But because eventually when you rotate your terminal ray up, you lose your right triangle, we actually reach 1. Same thing with cosine, which is adjacent over hypotenuse. your adjacent will never be larger than the hypotenuse, so we never surpass 1. So the range for both of those is between -1 and 1. Now, because you know more than the textbook thinks you know at this point because you've taken Algebra 2, you also know that the sine curve starts at 0 and does this, right? And it oscillates back and forth between -1 and 1. Correct? And that obviously continues. That's your sine curve. Your cosine curve also oscillates between -1 and 1, except for it starts at a maximum. That's really like the parent graph, but then this pattern also continues. So you know from that graph about the having to stay in between -1 and 1. But I also drew those because based on what you know about symmetry and even functions versus odd functions, a sine curve is even, odd, or neither. Even would be symmetrical to the y-axis. Odd would be symmetrical to the origin. Neither would be symmetrical to neither. Andrew? Odd. That's symmetrical to the origin because it looks the same right side up as it does upside down. Like, for example, watch me as I flip it. It starts at 0, 0, and it goes up through the first quadrant. If you flip it upside down, it starts at 0, 0, and it goes up through the first quadrant. So it's the same right side up as it is upside down. How about cosine of x? What's that? Even, odd, or neither, Sarah? Even, because it's symmetrical to the y-axis. Now the tangent graph we didn't think about. We didn't talk about domain and range yet. We can in a minute. What kinds of values can you not take a tangent of? We already saw one on these notes where tangent was undefined. Con. Right. Can't be on the y-axis. So a pi over 2, or a 3 pi over 2, or a 5 pi over 2, or a 7 pi over 2. So odd integers preceding a pi over 2 will be a problem. So I'll just put an asymptote at pi over 2, at 3 pi over 2, at negative pi over 2, and so on. And then, if you remember the tangent graph, I don't know how much of these you did. I would think you at least saw or were exposed to them a couple times. Does that look familiar to you? I've never seen a tangent graph on the regions, but we usually just show them to you because we know that they're important moving forward. And that pattern is just going to repeat. So what is, well, the domain then, I'm going to say if h of x equals tan x, the domain is x can be any real number except x cannot equal k pi over 2 when k is odd integer. So k could be 2. 2 pi over 2 is not a problem. But 3 pi over 2 is, and 5 pi over 2 is, and every odd pi over 2. And the range is what? What do you think, John? What's the range of this graph? Yep, negative infinity, positive infinity. Okay, so just jumping back one step here to this section that we oh, actually, no. Is tangent even or odd? Or neither? Even, odd, or neither? Bailey. Who are you asking? Me? Classmates, can you answer her? Is it odd? Classmates, you're leaving her out to dry. Is it odd? You have a lot of people saying no. Does anybody else agree with her that it's odd? Nobody, Bailey. Shame on them because they're wrong. You were right. It is odd. Yeah. Well, look at it. It's not symmetrical to the y-axis, right? But look at it right side up for a second. It starts low, goes through the origin, and then goes up. Well, if you flip it upside down, here's the y-axis. It starts low, goes through the origin, and goes up. It looks the same right side up as it does upside down, which means it's symmetrical to the origin, which means that it's odd. So what this section right here is getting at is we do know another way of finding these values. But pretending that we don't know how to assess the quadrant and the reference angle and all that stuff, just strictly based on the fact that cosine is even. If you're an even function, then when you plug in a negative x value, it should give you the same thing as you would get if you had plugged in the positive value, right? Cosine of negative x should equal the original cosine of x. And that value, anybody remember what the cosine of 45 degrees was? Because if there's a 45-degree angle in a right triangle, what kind of right triangle is it? If there's a 45-degree angle in a right triangle, what kind of triangle is it? What'd you say? Not equilateral. Close. Equilateral is 60, 60, 60. Isosceles. And I don't know if you guys remember your ratios. You probably don't, because I think they're not in geometry anymore. But I'll tell you, in a 45, 45, 90 right triangle, if your two legs are x and x, your hypotenuse is x root 2. So if I wanted the cosine of 45, I would do my adjacent x over my hypotenuse x root 2. And obviously your x's will cancel and you have 1 over root 2. And then you rationalize and you get root 2 over 2. Does that sound familiar now? Cosine of 45 is root 2 over 2. And the tangent of 45, do you remember what that was? What would the opposite over the adjacent give you in an isosceles triangle? 1. Same over same. At any rate, because this is odd functions say that the tangent of negative x is the same as the negative tangent of x. And since the tangent of pi over 4 is 1, this would just be negative 1. So for right now, I'm not making you re-memorize the values, but I am making you memorize what happens in an isosceles triangle. That is right. And that is the sine of pi over 4 is root 2 over 2. The cosine of pi over 4 is also root 2 over 2. And the tangent of pi over 4 is 1. So you don't yet have to memorize the entire table, but those three, and also their reciprocal versions, you are responsible for knowing right now. Because they come from isosceles triangles, and because the ratio of isosceles triangle sides is x, x, and x root 2. I keep saying isosceles triangles. I should be saying isosceles right triangles. Doesn't it make sense that the sine and the cosine should be the same value? Because opposite over hypotenuse versus adjacent over hypotenuse is both x over x root 2. All right. Back to your reciprocal stuff. So sine is the reciprocal of cosecant, so I'm just kind of showing you, because there is a way of writing that sine, because we know sine is opposite over hypotenuse, I wanted you to realize that we're not really referring to this. We're referring to what is this the reciprocal of. So sine is the reciprocal of cosecant, which is, in order to write the reciprocal of something, you just put 1 over it or flip it. The reciprocal of cosine is secant. The reciprocal of tangent is cotangent. Then vice versa, cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. Now I also wrote tangent and cotangent in a different way, because tangent, for the same reason that tangent is the y coordinate over the x coordinate in this scenario, tangent is equal to the sine over the cosine. So for tangent of t, I'm putting sine t over cosine t. And therefore, if cotangent is the reciprocal of that, it would be the cosine t over sine t. So just so those are laid out. In the next one, so we'll actually use this stuff. If the sine is 2/5 and the cosine is root 21/5, find the value of each of the 4 remaining trig functions. So sine, cosine, tangent is the next one we can give, which is just that sine value of 2/5 divided by the cosine value of root 21/5. To simplify, we would keep change flip. Your 5s cancel. 2 over root 21. Rationalize would be 2 root 21 over 21. So there's our sine, cosine, and tangent. To jump to cosecant, we're just going to flip the sine into 5/2. To take the secant, we're just going to flip the cosine into 5 over root 21. And then we'll rationalize into 5 root 21 over 21. And then for the cotangent, let's be smart about this. I'm not going to flip-flop this one, because prior to rationalizing, here's what the tangent equaled. And if I just flip this version and put the root 21 on top and the 2 on the bottom, I don't have to re-rationalize again. So, just out of curiosity, to get you to make a connection, what quadrant is this angle T in? 1, 2, 3, or 4? Abby? And how do you know? Right. Everything's positive, so it's in quadrant 1. In the next exercise, they're giving us the sine value of 3/5, which is positive. And then what quadrant are they telling me T is in? Joey, what quadrant is T in if it's between 0 and pi over 2? What are you thinking? The first, right, because here's 0, here's pi, so this is half a pi. So if T is between 0 and pi over 2, it's in the first quadrant. And the sine is 3/5. This wants to find the value of cosine, and you do need to sketch a graph. Well, there's two ways you could do this, I guess. I typically like to draw a picture. If I know it's in the first quadrant, just draw a terminal ray in the first quadrant, drop my altitude, here's my angle T, and then the opposite is 3 and the hypotenuse is 5. So if I've got 2 of the 3 sides of a right triangle, I can find the third. Morgan, what would this side length be? Or how would you find it? Right, so something squared plus 3 squared equals 5 squared. You should know your Pythagorean triples, it's a 4. 3, 4, 5. So now if they want to know the value of cosine, that's adjacent over hypotenuse. Do you guys remember the trig identity, sine squared plus cosine squared equals 1? You remember that? Sine squared plus cosine squared equals 1? So I could also use that. 3/5 squared plus cosine squared equals 1. Subtract 9/25 from both sides, because that's what 3/5 squared is. 25/25 minus 9/25 is 16/25. I take the square root of both sides, and the cosine of t equals plus or minus 4/5. How did I know it was positive and not the negative? Because I'm in quadrant 1, and cosine has to be positive. So when they said using a trig identity, that's the version and the method they were talking about. Okay, and the last thing here. Essentially, this is just getting at periods. How frequently does the sine curve repeat itself? How long does it take to get one full cycle in? Do you remember? 2 pi. The same is true for cosine. 2 pi. What is it for a tangent? From negative pi over 2 to positive pi over 2? What's that? Nope. From negative a half pi to positive a half pi. Just pi. Okay, so that period is just pi. So on these two questions, what they're getting at is, so you can fill that in, 2 pi and pi. If you want to find the sine of 9 pi over 4, you can find the sine of its coterminal angle just by taking off a 2 pi, which would be subtracting 8 pi over 4, which would be the sine of pi over 4, which is root 2 over 2. Whereas for a tangent, you can just add 1 pi. So I can add 4 pi over 4, and that'll be the tangent of negative pi over 4. And if I still don't like that, I can add another 4 pi over 4 on. And that would be the tangent of 3 pi over 4, which is a reference angle of pi over 4. And so its value is 1. But what quadrant are we in? 0 pi over 4, 4 pi over 4. So where's 3 pi over 4? First, second, third, or fourth? Second. So tangent should be negative. Your homework obviously is there at the bottom.